Hello everyone, this video is about Riemann sums. It's the second video about Riemann sums. In the first one we did Riemann sums from equations and also from graphs. In this video we're going to focus on Riemann sums from tables, and we're also going to talk about two other things: Riemann sums in summation notation, and we're going to now move to finding the exact area by thinking about how we can make a Riemann sum into what we call a definite integral. So beginning with the Riemann sums from tables, first example says, find the right Riemann sum and the trapezoidal Riemann sum using 4 subintervals for the function f, which is continuous and positive on the interval 0 to 12. And then we're given the table. So first thing is to make sure we understand where our x's and y's are. These are x values, so x is equal to 0 is here, x is equal to 12 is there, and these in the middle are x equals 2, x equals 5, x equals 10. The y values are here. These green numbers down here are the y values. And something very important to understand in a table problem is that if we were to picture the information that we have been given, we've been given that we have a function f, and we know its y value at 0, f of 0 is 16, so maybe 4, 8, 12, 16. We have 1 point on this f graph here. We have a point at x is equal to 2. We know that the y there is equal to 12. So maybe I'm here at 12 if this is 16. And then I jump to x is equal to 5. Notice it's not 4, right? It's 5. So the spacings here might be different. So at 5, at x is equal to 5, y is equal to 10. So I'm here somewhere. And then x is equal to 10 out here. I'm at y is equal to 12 again. And at x equals 12, which is out here somewhere, y is equal to 8, right? So this is all that we know about this graph. We, of course, we do know that it's continuous and that it's positive, which means there are no breaks, there's no like asymptote in between those points, there's no holes as the function goes through those points. But we don't know very much other than that. We just know that it's continuous and it's positive. You cannot decide to connect these points in lines to think about the problem. That is not necessarily true about the function. You cannot decide exactly what shape is happening in between these points. We really don't know. It could be anything. It could be that, or it could be that, or it could be basically an infinite number of possibilities, right? So basically, we want to remember this. Don't make any assumptions about what the function is doing in between the points that you have been given. Okay, so now that we have that clear, let's think about the right Riemann sum R4. The way we would set this up is first rectangle will go from 0 to 2. The right end of that rectangle is 2, so the y value would have to be 12, and this would be my first rectangle. Second rectangle sits from 2 to 5, and I need the y value at 5, which I have in my table, so this would be my second rectangle. Third one sits from 5 to 10. I go up to the y value at 10. And this would be my third rectangle, and the fourth one sits from 10 to 12, and so that would be my fourth rectangle. So now notice the partition is unequal, because these delta x's are not equal, the widths of the rectangle. So notice that. But we have everything we need in order to do the R4 sum, because it would be 2 times f of 2 plus 3, which is 5 minus 2, right? This delta x here is equal to 3, 5 minus 2, right? Notice in the table, it's this number minus this number. 5 minus 2 is 3. 3 times the y value at 5, so 3 times f of 5, plus this 10 minus 5, which is this width right here, 5 times f of 10. And then the last one is 2, 12 minus 10, right? This is 2 times f of 12, because I'm going to the right end of each rectangle. So the y values that I've used are f of 2, f of 5, f of 10, and f of 12. In a right Riemann sum, the leftmost y value, which is in this case f of 0, right, doesn't come into play. So this is my setup. So we want to be able to write that equation and then put in the numbers. 2 times 12 plus 3 times 10 plus 5 times 12 plus 2 times 8. And if you do this correctly, it's 24 plus 30 plus 60 plus 16, which comes out to be 130. You can pause the video and try a left 4, L4 Riemann sum, and that would look like this. L4, for L4, I'll show it here in another color like yellow. The widths of the rectangles would be the same, so the first one would be 2, but I'm going to the left edge to get the height, right? So the first rectangle would be like this, and the second one, the width would be 3, and the height now would be 12, and then the third one would go from 5 to 10, and the height would be 10, and then the fourth one would go from 10 to 12, and the height would be 12 again, right? So with the left Riemann sum, it would be 2 times f of 0 plus 3 times f of 2 plus 5 times f of 5 plus 2 times f of 10. This would be our left Riemann sum, and if you plug all of these numbers in, you would be doing 2 times 16 plus 3 times 12 plus 5 times 10 plus 2 times 12, and I think this answer would be 142. Okay. The trapezoidal Riemann sum would go like this, that this is called T, so we're doing the trapezoidal now, T4. So for the trapezoidal sum, remember that, let me just erase these here so that we can think about the trapezoidal sum. So for the trapezoidal sum, we have the same points, are all we know about the function, right? And so we are here, we'll put the points again in red. So we've got a point here and a point here and another point here and then back here and then something like this, right? So these are my points. This is all I know. Trapezoids are going to sit like this. The first trapezoid is going to be base 1, base 2, height of the trapezoid, and connect, right? That's the first trapezoid, and then the second is going to look like this. The trapezoidal sum is going to be 4 trapezoids, right? And for each one, it's going to be 1/2 of b1 plus b2 times height, like we did in the last lesson. The 1/2 is going to come out front. The h in this trapezoidal formula means the delta x, right? Now, we're not able to pull out a common delta x, so I just have to keep, I've got to keep it, each trapezoid separate within the parentheses, and it would be the first trapezoid, the base 1 is f of 0, and the base 2 is f of 2. So it'll be f of 0 plus f of 2 times the first trapezoid height, which is 2, plus f of 2 plus f of 5, that's the sum of the next two bases, which are these two, right, times the second height, which is 3, plus f of 5 plus f of 10 times the third trapezoid height, which is 5, and then the last one is going to be f of 10 plus f of, I'll write it down here, f of 10 plus f of 12, right? And the last trapezoid has a height of 2. So this would be my trapezoidal sum, and you would put all of these numbers in and do it carefully. And the answer we're going to get for T4 is going to be 136. Okay. So let's go on, pause the video, and try to do example 2. We're looking at selected values of f in the table, and we're using the table to compute the left Riemann sum and the midpoint Riemann sum for 2 to 62, that's an x interval, and we're trying to use as many subintervals as possible. So let's begin with the left Riemann sum. So L6, pause the video and see if you can write down the setup and the answer. L6 is going to be, here are my delta x's, right? Delta x for the first rectangle width is 10, and for the second is also 10, and for the third is 10, and 10, and 10, and 10. So all these delta x's are the same. Delta x means the rectangle width, and I can pull out a 10. Okay, this next problem is the broken odometer, which means odometer is a dial or a meter that reads the distance traveled. This is distance traveled. And speedometer is the one that reads the velocity, right? So they're saying, imagine that you have your odometer is broken, but you still want to know your distance driven or traveled over this 30-second time interval that the table shows. And then they're saying the table is showing you the speedometer or the velocity readings from 0 to 30 seconds, right? So here's 0, here's 30, and we have it every 5 seconds. The table is showing us the velocity at that instant, right? And we are being asked to find the distance traveled, right? So if you think about what's going on graphically, we are, every 5 seconds we have a reading on this table, 5, 10, 15, 20, 25, and 30. And we're saying, okay, at time 0, I'm going at 25. So I'll use 1 tick is 5 feet per second, so 25. And then at 5 seconds, I'm going at, I think it said 31, right? So I'm somewhere here. I'm going a little faster. And at 10 seconds, I'm going at 35. At 15 seconds, I'm going at 43. At 20 seconds, I'm going at 47, and then back to 45, and then, 45 be here, and then down to 41, okay? So I know that these are my instantaneous speeds at each, or velocities. This is at each of these instants in time. I know those are my velocities. But I'm not allowed to assume anything in between. I do not know that I'm going in a straight line or a curve, or I have no idea what is happening in between, right? Do not know, right? Do not know. So don't make any assumptions to do the problem. And we're then asked to estimate the distance, right? So a reasonable way to estimate this distance would be to say, I can just use a Riemann sum type of idea, which means I'll just say, for these first 5 seconds, let me just assume that I'm going at 25 the whole time, right? I know I'm not, but this will be my first estimate. This area here, 125 feet is how far I would have traveled in those first 5 seconds. It's not accurate, maybe. It's not exact for sure, but it's not bad, you know, it's something to go with. For these next 5 seconds, I'm going to assume I just go at 31 the whole time, right? This is 31 here, so I'm just going to assume I go at that, and I'm going to do my second Riemann rectangle. This I'm doing a left Riemann sum. The third rectangle, I'll just assume I just went at 35 for that whole stretch. And then the next one, I'll assume I went at this speed for the whole stretch. And the next one, I'll just go like this. And the last one, I'll assume I went at 45, I'm sorry, for that whole stretch here, okay? So the point is that I know that that's not true, that in these first 5 seconds, I'm going at some other velocities at each different instant, but this is a good way to estimate my total distance traveled, right? And then I would get that my total distance traveled is the sum of all those rectangle areas, right? Like this first one is 125, 25 times 5, and then I'll have 31 times 5, which is 155, and then I'll have 35 times 5, which is 175, and so on, right? And I'll add up all of these, and I'll have my total distance estimate. So the Riemann sum here would look like L 6, the way I wrote it, right? And that's equal to 5 times, I can pull the 5 out, 25 plus 31 plus 35 plus 43 plus 47 plus 45, and this will be 1,130 feet, right? Notice my units, if velocity is in feet per second and distance is in seconds, when you multiply those, the seconds cancel and your answer is in feet, okay? So you can also do a right Riemann sum to estimate this, and you can pause the video and do it and then check your answer. Your answer for the right Riemann sum should be 1,210 feet. If you do a midpoint sum, you have to do 3 subintervals, and you would then have to take a delta x, or you'd be saying with a midpoint sum that you're gonna say for these first 10 seconds, right? We're traveling at this velocity here at whatever the velocity at the midpoint is, right? In this case, 31, right? So for a midpoint sum, you just have 3 rectangles like this, and you'd be using the middle x value to get your height for the rectangle. So it would look something like the yellow guys for your midpoint sum, and that one would be 10 would be the common width that we pull out times 31, right? So 10 and then the middle y value, 31, plus another 10 times 43, this middle y value, and then 10 times 45. This middle y value. And so final answer there would be 1,090 feet, 1,190 feet, okay? And that's an estimate as well, okay? So these are all ways to estimate the distance traveled. Okay, now example 4 is very similar to 3. So we are talking about a car that stops at a toll booth and then proceeds onto the turnpike. The car's velocity is in meters per second at various times t from 0 to 30. So we have the velocity at exactly 2 seconds is here, and at 5 seconds is here, and so on. And we are assuming that the velocity in this problem, we're assuming that if you did know the graph in between 0 and 2 seconds, it would be increasing, right? We're assuming we're increasing the whole way. Because the car is speeding up as we enter the turnpike from an on-ramp. And then they're asking for a lower estimate and an upper estimate. So you do it exactly the same way as example 3, except we have to realize that if the velocity graph is increasing, then the lower estimate is going to be the left estimate, because if you make your rectangles using the heights from the left end of each rectangle, the whole Riemann sum is going to be inside or under the curve. That's going to be your left. Your left is going to be your lower or under estimate, and your right estimate, which means you're going to use the heights at the right end of each rectangle, right? That's going to make your rectangle stick out over the graph, and so that is going to be your upper or over estimate. Okay, so then this answer, when you do it, I'll just give you the final answer here. You're going to do L7 for the underestimate, L7. And that's going to be, oh, careful here, by the way, just another note. These delta x's are not the same. So you have to do 2 times 0 plus 3 times 2.2 plus 3 times 4.5, right? 3 times 4.5, 3 times 2.2, 2 times 0, like that, plus, I'll just write it all out, 2 times 9, this is the left one, plus 5 times 13.4, plus 10 times 16.5, plus another 5 times the last piece here, which is 20, right? And this whole thing was going to give you an answer of 370.1 meters. For the right one, you're going to go to the right end of each rectangle, right? So R7 will be 2 times 2.2 plus 3 times 4.5, and so on, right? I'll just dot that one. And the last one for that case would be this last rectangle would be 5 times 22, right? Because we would use this because it's the right end of the rectangle. Final answer here would be 464.2 meters, right? This would be the upper, and the lower was 370. The exact area, if you actually knew the curve, the exact area under that curve will be the distance traveled, and it has to be between these two estimates, lower and upper. Okay, so in both of these examples, in examples 3 and 4, the area under the velocity curve was used to estimate and to add up. And just here, I want to give you another word for add up. Another word for add up is accumulate. So the area under the velocity curve was used to estimate and to accumulate changes in position, right? And we can say that in general, a Riemann sum for an f prime graph, right? In this case, velocity is equal to s prime. Position is s, velocity is its prime, right? So a Riemann sum for an f prime or a rate graph, and f prime is usually a graph of a rate, that can be used to estimate and add up or accumulate changes in f, right? So area under the f prime graph has this meaning of change in terms of f, and a Riemann sum allows us to add up changes in f and find like a total change in f. Okay, so this is the idea here, and let's move on now to Riemann sums in summation notation. Okay, so Riemann sum in summation notation. Quick review of summation notation. Summation notation means, you know, here's a counter, here's a starting value for the counter, here's a stop value for the counter. The sigma itself basically means sum or add up. It's all the plus signs. And then this right here is a rule. The rule is going to be expressed in terms of whatever the variable for the counter is. Okay, so summations can be written in summation notation, like this right here, the sigma notation. We can also expand this, right? So you start at the starting value of the counter, and then you keep stepping the counter up using the rule, and you stop that at the ending value or the stop value of the counter, right? So this is called the expanded notation. And then we can actually go ahead and add these numbers up, right? And that would be evaluate. If you were asked to evaluate that series or that sum, it would come out to be 4,950. This one, this by the way is called the linear series because it's just, you know, the rule is a line. Okay, this one, j squared, right? The rule is quadratic, so this is going to be a quadratic series, and it goes 1 plus 4, because when the counter is 2, when j is 2, then j squared is 4, plus 9, plus 16, plus dot, 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 and we'd stop at 15 squared, or 225. And this comes out to be 1,240. That's a quadratic series. Now, people have figured out certain formulas for adding a linear series. So this first series will always work out to be n, which is the stopping value of the counter, times n plus 1 divided by 2. And the quadratic series will always end up being n times n plus 1 times 2n plus 1 divided by 6. Okay, so let's check that out, right? So I'm saying that if you took a calculator and sat there and added all these up, we know we would get this number. You would get the same number if you took the top stopping value of this counter, which is right here, 99, and if you did 99, so now I'm using this n times n plus 1 divided by 2, 99 times 100 divided by 2 is also the same answer. Okay, so we figured out that if the series rule is just I, then it's always going to work out that way. For the quadratic series, this is the same as if we took this 15 on the top, and if we did 15 times 16, right? So n times n plus 1, sorry, 15 plus 1, which is 16, times n 2n plus 1, which would be 31. All of that divided by 6. The 6 is from here. If we did that, we would get this same number, 1,240, because this is a formula for the quadratic series. Okay, why am I talking about series? I'm talking about series because Riemann sums are just begging to be written in series notation, right? Because what are we doing every time with a Riemann sum? Let's just think about this. We're starting at some x0, right? And this is A, right? And then we're going all the way until B. And then we're making rectangles, you know. We have one rectangle and then a second one. They might be of equal width or unequal width, but they're sitting in here all the way from A to B, right? So here's my first rectangle, and its width would be called delta x1. Here's my second rectangle. Its width would be called delta x2. Here's the next one, delta x3 is the width. Delta x4, delta x5, right? And I could go on. I just drew 5, but I might have however many. I might have n of these, right? And then we're going to just write these type of formulas for a right Riemann sum. What we're saying is that this place here is going to be called x1. The right end of the first rectangle is going to be x1, and then x2, and then x3, and then x4, and the b is going to be x5 in my picture, but in general it's going to be xn. Okay, so a is x0, b is xn, and in between I have all these other x's, which are the right edges of each rectangle, and we know that we go up to f of that x value, and that's how we get our height. So here's my height of the first rectangle and my width of the first rectangle, right? This is rectangle 1. And then I have height width again for rectangle 2, right? And so on. And you can see the counter or the subscript here is changing from 1 to 2 to 3, right? So height times width until I get to the last rectangle, and this is the height and the width of the last rectangle, the nth rectangle, okay? And that's a Riemann sum. And this can be very conveniently written into summation notation like this. We're adding up, that's the sigma, n rectangles. First rectangle is the first one, nth rectangle is where we stop. And inside the Riemann sum, I have each of the rectangles, I have the height of rectangle and the width of rectangle, right? And I keep them straight by the counter, which tells me which rectangle I'm on. Okay, so it's a very convenient way to write a Riemann sum. Okay, so using this new way of writing a Riemann sum is going to help us to go from the estimate, right, which a Riemann sum we know is an estimate. I want to take it a notch up and actually get the exact area, right? So this sigma notation is going to help us do that. Let's see how that works on that initial problem we did in last class, which was y is equal to x squared, right, going from 0 to 1. And say I wanted to find, now I'm not satisfied with estimates. I know how to do those with different Riemann sums. I'm really after now the exact area, right, which is the question we posed at the very beginning of the Riemann sum lesson, the first one. So how can we do this? Well, as we've mentioned here and there, if you're going to make more and more rectangles, right, imagine that instead of having just 4 rectangles here, I had, 20 little rectangles in here. I'm not going to draw exactly 20, but I have a lot of rectangles in here, and I'm going to do my Riemann sum with this many rectangles. You can see that if I increase the number of rectangles, then my error, the overestimate in this case, the way I'm drawing it, will be less, right, if I have more rectangles. So that's really how we're going to get at the exact area. We're going to say, I'm going to take this Riemann sum that I just developed, I equals 1 to n f of x sub I delta x sub I, and we're going to take a limit of this as n, the number of rectangles, gets bigger and bigger and bigger. I'm going to make the number of rectangles basically go to infinity, and that will then give me an exact area. Okay, so let's just do some notation here. So 0 is my A, we called it A, and this one was B, right? We're also going to call the A x0, and the B is going to be called xn, right? It's where the nth rectangle is going to end. Okay, in between I have all these rectangles, right? The first one is going to stop at x1, and the second is going to go from x1 to x2, and then x3, and then x4, and then dot, 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 right? All of these. The width of the first rectangle is going to be delta x1, right? That's the width of the first one, and then the second one, delta x2, and so on, dot, dot, dot. Okay, so now for this particular problem, delta x, I'm going to use an equal partition. 1 minus 0 is the whole distance, and I want n rectangles. So my delta x must be 1 over n. Okay, the x sub i's, like the x1, is going to be 0 plus 1 delta x, and that's 1 over n, because delta x is 1 over n. x2, when I'm at the right end of the second rectangle, that means I started at 0, but I've gone 2 rectangle widths out, so now I'm at 2 over n. x3 will be 0 plus 3 delta x, which is 3 over n, right? And so you're seeing the pattern. The pattern is, this is my counter I, so x sub I is going to be equal to I, right? Here's my I over n for whichever rectangle I'm on, right? X sub I is going to be I over n. Okay, now let's think about f of x sub I. Well, we know that f of x, the rule for this graph is squaring. So f of x sub I is I over n, the quantity squared, or I squared over n squared. So we have everything we need, right? We have delta x, which is 1 over n, and I can say delta x sub I is 1 over n because any of the rectangles has that same width in this case, right? So I'm going to put all this back into our Riemann equation here. So it's the limit as n goes to infinity. This is what I'm trying to do of the sum of all these rectangles, where f of x sub I is I squared over n squared, and delta x sub I is 1 over n. Okay, we're almost done, guys. Stay with me. Okay, so now here's the cool thing. What we're noticing is that this 1 over n cubed, right, because 1 over n squared times 1 over n is 1 over n cubed, that whole piece doesn't really depend on I. So I can pull that thing out of the summation, and I'll have this situation. Right? Because I only need whatever depends on I to be inside the summation. Okay, now guess what? This is that quadratic series that I showed you before, and so I know that it has its formula, which is n times n plus 1 times 2n plus 1. It will always work out to this sum, right? So I can write this whole blue thing as this right here, okay? And now we can actually find a limit. It's like, you know, it says n, but it's as if it were x's, right? So this limit right here is going to work out like this. This limit, oops, wrong color, limit as n goes to infinity of this, we can cancel out 1n, and I'll have a 6n squared on the denominator. And if I FOIL out the top, it'll become 2n squared plus 3n plus 1, okay? And guess what? I mean, that is just like saying the limit as x goes to infinity of 2x squared plus 3x plus 1 over 6x squared, right? And we're going to see that we have an equally heavy polynomial right here. And so the limit is going to be the ratio of the two leading coefficients here, which is 2 over 6, right? So this limit, wow, finally comes out to be 2 over 6, or 1/3, right? So that was a lot of work, but the reason we're doing it is because guess what? We have now the exact area under a curve. This is a pretty big deal because as you can see, right, I mean, how do you actually find that exact number? Well, we found a way to do it. And the way to do it was to take the Riemann sum and imagine the number of rectangles going to infinity or becoming, you know, growing without bound, and do a limit problem. And that's how we found the exact area under the curve. Okay, so this limit value of the Riemann sum, as the number of rectangles goes to infinity, we can now say gives us the exact. We have gone from estimates to exact by doing a limit. Should ring a bell. It's like what we did in the fall as well, right? There we went from estimating the rate of change with the secant line to getting the exact rate of change by finding the tangent line slope. Here, same idea with areas. And this limit value of the Riemann sum is so important that it has its own name. It is called a definite integral. Okay, so definite integral is here in the box. We've just understood that the limit takes us from an estimate to an exact. So this is the exact area. If you have an equal partition, then we can say a couple of other things, that the delta x sub I will be b minus a over n. The x sub I will be a plus I delta x, just like we did in the example. And we can write this equation like this. We can say all of this is the same as up there. And then this x sub I here, I can replace it with a plus I delta x, right? So I can do a plus I delta x for this piece here. And delta x sub I, we might often drop the I because we are working with an equal partition, right? So it doesn't matter. We don't have to, for the widths are all equal. So we don't have to number them in terms of the rectangles, right? So I can write my area like this, exact area. And this exact area is going to be called, or going to be also called a definite integral, right? So this right here is the definite integral. And that's the meaning of the definite integral, is that it is a limit of the Riemann sum. And in terms of the pieces of this, let's see if we can do a little bit of color coding. This whole thing right here, the limit of the sum, right? That's what now became the integral, right? That's the integral. And then the a is our starting value for x. The b here, this b is the ending x value, right? So this is my ending x value for the Riemann sum. And then f of, well, let's see, this dx right here. The dx becomes, or the delta x becomes a dx, right? And a plus I delta x, right? These, which are really x sub I, right? If you look at the top equation here, we set it as x sub I. The x sub i's, because I have so many of them, we don't need to count them anymore. They just become x's, right? So the x sub I is what becomes, this whole thing is x sub I, right? That becomes x. Okay, so this is how we translate between Riemann sum and an integral, and we're going to work on that next video. And here it is again. So pause the video and do the takeaways. So the takeaways, R10 would estimate the area between the graph of f and the x-axis using 10 rectangles. When finding Riemann sums from tables, the rectangle widths are found by subtracting consecutive x values from the table. Rectangle widths may be equal or unequal. We saw that with our table problems. Physically speaking, a Riemann sum uses the rate function, right, the f prime, to calculate and add up or accumulate small changes in f. Okay, a Riemann sum can be written in sigma notation, so we can start our counter at 1 and stop at n, and that means n rectangles. The sigma means we're adding up the areas, and f of x sub I is the height of the ith rectangle, and delta x sub I is the width of the ith rectangle. I is going to keep track of which rectangle. The exact area can be found by taking the limit of the Riemann sum as the number of rectangles n goes to infinity, right? Which means delta x goes to 0, right? It's like saying I have so many rectangles that each one is like kind of like a matchstick, has no width. Okay, so here we have the integral now, the definite integral. It's going to be the subject of our studies for a while now, and this just means we've done a Riemann sum from A, right? Start at A, end at B, and we have taken the limit of that Riemann sum by making the n number of rectangles go to infinity. Hope you had fun with that. This was a very big deal in the history of math, so I hope you enjoyed learning about exact area.